Welcome back to week 3 of our course, Boltzmann Law, Physics to Computing. This is the second lecture for this week. Now, in the first lecture, we introduced this concept of a transition matrix. And we saw how you could calculate the stationary probability distribution by finding the eigenvectors of this matrix, whose eigenvalue is 1. Now, what we'll be talking about in this lecture is what's called Gibbs sampling. And basically, it is this principle of sampling that we have been using in week 2, the one that I introduced in the very first lecture of week 2. And we'll see how to write down the transition matrix for this kind of sampling and why some forms work and some forms don't work. So this is what we'll be actually talking about in this lecture and the next. Now, so how does this Gibbs sampling work? Well, the idea is that you go to one of your neurons. So what I'm showing here is a set of, say, 6 neurons, which have some probability of being 0 or 1. And when you're trying to go from time step t to t plus 1, what you do is go to a particular neuron, say the rth one, and either set it equal to 0 or equal to 1 according to a certain algorithm that we'll be talking about in a minute. But the point is, at any step, you only update one neuron. You don't mess with the rest. So in that sense, at any point when you're working on the rth neuron, your choice is, you just have 2 choices. You can either set that neuron to 0 or set that neuron to 1. And you're not supposed to mess with the other ones. The other ones remain wherever they are, whatever configuration they may be in. So that configuration of the other neurons we'll call alpha. So that our choice is between alpha 0, meaning rest of the neurons in alpha and the rth one in 0, or rest in alpha and the rth one in 1. And when we try to write down the W matrix, that's the transition matrix, we are basically trying to write down this 2 by 2 section. Note, of course, that the matrix itself is much bigger. You see, even with 6 neurons, the matrix would be 2 to the power 6 by 2 to the power 6, which would be 64 by 64. And in general could be even bigger. Depending on what the number of neurons, it grows exponentially. But for this method of sampling, when you're dealing with the rth neuron, the only non-zero elements are in this 2 by 2 block, alpha 0 and alpha 1. And how do you fill up this block? Well, the procedure is you first find this quantity that we called x tilde, which you obtain from the difference in the energies between the 2 possibilities, 1 and 0. And that is what, as we discussed, you could write also as the derivative of the energy function. And that's because s is a binary variable, and so s squared is equal to s. And so we always are dealing with linear functions. And in that case, the difference between the value at s equals 1 and s equals 0 is the same as like taking the derivative. I should also mention that in general, you often calculate this x using this synapse equation. And what we are doing here is kind of equivalent. In fact, this is more general because it would work even if energy functions had higher order terms beyond quadratic, as we have discussed earlier. But later when we do another example, I'll show you that you get the same answers whether you do it this way or this way. But for our purpose now, it's much more convenient to do it from these energy differences. Now, what do you do once you have the x? Well, you find the Fermi function of that x. And the Fermi function is the mirror image of the sigmoidal function. The sigmoid function is something you see a lot in the neural network literature. And the Fermi function is what you normally see in, I guess, solid-state devices and solid-state physics courses. And the Fermi function is like the mirror image. So it's a sigmoidal function of the negative of x. The Fermi function goes from 1 to 0 as x is increased, whereas a sigmoid function goes from 0 to 1. Okay. Now, once you have this Fermi function, the rule is that the probability that this neuron will be set to 1 is equal to the Fermi function. And note that this probability is independent of what the neuron currently is. That doesn't matter. You just calculate x tilde, find f, and then depending on f, you set it to 1 or 0. And so, remember, when you write the W matrix, the columns correspond to the current state, the state at time t, whereas the rows tell you the state at time t plus 1. And so, since the state at time t plus 1 really doesn't depend on the state at time t, we put f on both columns here. Similarly, if you want to write the probability of putting a 0 on that neuron, well, that's 1 minus f, and again, it's the same for both columns. And finally, one property I had mentioned of transition matrices is that every column must add up to 1, and it does. That's trivially clear. But of course, you might wonder that, well, you know, you told me W was a huge matrix, and we were just writing this little 2 by 2 block. But it's that huge matrix where the columns should add up to 1. That's true, but the way we are doing it here, all other elements of that matrix are actually 0, because in a particular step, the only element that can change is the rth neuron. Okay? And so if these add up to 1, it means the entire big matrix also would add up to 1, the columns. Okay. Another question you could ask is detailed balance, because if you remember, in the last lecture, we said that one way to ensure that the W matrix will give a stationary distribution that matches the Boltzmann distribution is to ensure this detailed balance, that Wj to I and Wi to j are in the ratio of this exponential, where with these energies for j and I. And the question is, what we wrote down here, does that satisfy this condition? Well, we can check. See, our j and I are basically the alpha 1 state and the alpha 0 state. So the question is, what is the ratio of the rate from alpha 1 to alpha 0 as opposed to alpha 0 to alpha 1? And you'll notice what we have written down is 1 minus fr for the numerator and fr for the denominator, as you can see from your matrix. And what's this equal to? Well, we have fr, we have this expression, and what you can show is 1 minus f over f is actually exponential of x. How do you show that? Well, just a little bit of algebra. You'll notice this expression is really 1 over f minus 1. And 1 over f means the denominator. And when you take away 1, you're left with the exponential. So you can do this yourself. It's a bit of algebra, but yeah, you get this is equal to the exponential. And what is this exponent? Well, it's the energy difference. So I could write this as exponential of minus E alpha 0 minus E alpha 1. And as you can see, we have basically proved this detailed balance, because after all, I is basically alpha 0 and j is alpha 1. So detailed balance is satisfied. Okay. Now let's look at a specific example with, say, 2 neurons. How would we write down the W matrices? Now we start, of course, with the energy expression, which in matrix form would be written like this. But with 2 neurons, you could actually spell it out, and it wouldn't be too inconvenient. The matrix version is particularly useful when you have lots of neurons, because it's hard to write out all the terms. But here, you could easily write this out, because this first term will give you these 2 things, S1x1 plus S2x2. And the interaction term will give you this W12, S1, S2. And note, of course, these are Boltzmann networks, where W12 is equal to W21, right? The W matrix. I mean, I should distinguish between the small w, which is the weight matrix, and this big W, which is the transition matrix. The small w is n by n. The big W is 2 to the power n by 2 to the power n. Different matrix. Anyway, so this matrix is symmetric for Boltzmann networks. The big W though is not symmetric. Now, from this we can write out the energies of all the configurations. How many configurations? Well, 2 neurons, so there are 2 squared, or 4 configurations. 0, 0, 0, 1, 1, 0, and 1, 1. So 0, 0 means S1 is equal to 0, S2 is equal to 0. And so we get 0. 0, 1, S1 is 0, but S2 is 1. Well, S1 is 0, so this term goes out. S2 is 1, so I pick up an X2. S1, S2 is 0, so I don't get anything there. So I get X2. Similarly, E10 gives me X1. And E11, that's when all 3 terms contribute. So you have X1 plus X2 plus W12. So those are the energies. Now we have to write down the W matrix, and I've put a superscript here to indicate that what we are doing is first we are updating neuron 1. Remember, the way this sampling works is we first update one neuron and then the next, right? And if you had many neurons, you'd go sequentially down the list. So now we are trying to update neuron 1. So when you look at these 4 things there, the point to note is that the second guy, the second neuron, is fixed. So from 0, 0, you can go to 1, 0. But you cannot go to 0, 1 or to 1, 1 because you are not allowed to change the second one. So when you write this W matrix, you'll kind of have these red question marks and these blue question marks. Those would be the non-zero elements. Rest will be zeros because the rest will require changing both neurons, and that's not allowed. In this sampling scheme, you update one neuron at a time. Okay. So let's just focus on these 2 first. How do we fill up this component? Well, we are basically talking about a transition between 0, 0 and 1, 0. So the corresponding x, this x tilde, is basically E10 minus E00. And that's really x1, as you can see. Now, you could have got the same answer starting from the synapse equation as well. Remember that another way of getting it for these linear synapses or quadratic energies is to find the x from this expression, from the bias term and the weight term. And if you do that and set S2 equal to 0, you'll get the same answer. But for our problem, actually, it's much more convenient to work with the energies. And so now that we have the x, you can define this Fermi function corresponding to this value of x, which is this energy difference, and fill up 1 minus F1 and F1. And you could also fill up this other column, that's 0, 0, 1, 0, this 1, 0, again exactly the same, 1 minus F1 and F1. Then you can go on to these blue ones, which involve a transition between 0, 1 and 1, 1. Right? And here, when you try to fill these up, the difference is that now we have to look at the energy difference between 1, 1 and 0, 1. So this and this. And that difference, you'll notice, is x1 plus W12. Last time the energy difference was just x1. And so this time, the Fermi function that will involve this quantity. And you could get the same result starting from the synapse equation as well. The difference is, again, now we'll put S2 equal to 1, whereas last time you put S2 equal to 0. But once we have this, again, we'll define a new Fermi function with a tilde, and this one, instead of x1, we have x1 plus W12 because it's the energy difference between the 1, 1 and the 0, 1. Well, that's how you now fill up those 2 columns, and we are done. So this is then the W matrix for updating neuron 1. keeping neuron 2 fixed. Now, is detailed balance satisfied? You can easily check it is, because the way we did it with F's, the last time we showed this detailed balance by taking this ratio of 1 minus F over F. Here also it works much the same way. Take 0, 0 and 1, 0, and if you look at the ratios, again is 1 minus F1 over F1, which has this correct dependence required by detailed balance. Similarly, if you look at the other pair, 0, 1 and 1, 1, same story. It's a different Fermi function, different argument there, x, but the detailed balance is satisfied. Okay. Next, we have to write down the W matrix for updating neuron 2, keeping neuron 1 fixed. You see, previously we updated neuron 1 with 2 fixed. Here we are going to update 2, but now with 1 fixed. And now you can see that the non-zero elements would actually be in this block here, upper left and lower right, because those are the blocks where the first neuron does not change. It's either 0 or 1. And so you can go ahead and fill them up. Again, much the same principles, but now the energy differences involved would be, in this block it would be between 0, 1 and 0, 0. In this block it would be between 1, 0 and 1, 1. But it's the same pattern, 1 minus F and F. So this would be then the transition matrix for updating neuron 2, keeping 1 fixed. And so collecting all the results, this is what we have. We have these 2 W matrices, one for updating 1, one for updating 2, and they depend on these various Fermi functions that appear, right? Each one corresponding to a different energy difference. Now, we have 2 choices when doing this kind of sampling. We could first update 1 and then 2, or we could update 2 and then 1. Now, if you do update 1 and then 2, then you should kind of take your probability distribution function, first multiplied by W1, that's updating 1, and then multiplied by W2. Note the order kind of looks opposite with respect to this. That's because it's the one on the right that you apply first, and then the one on the left. And that gives you the composite W for a complete set of updates. But if you update 2 and then 1, then I guess the W2 is on the right and then the W1. And once you have this W, then you could say that the way I'll find the stationary distribution is by finding the eigenvalues of W, and then one eigenvalue will be 1, and I'll look at the corresponding eigenvector P. So this is how you could then figure out that this kind of sampling, what stationary distribution will this kind of sampling yield? That's what this will show you. Now, I'll stop here for this lecture. What we'll do is continue with this in the next lecture, and we'll talk about what we get for the sequential updating the way we discussed, and then compare it with what you get when you try to update 1 and 2 simultaneously. Thank you, and see you back at the next lecture.